All right, in this section, 21 through 29, you're solving the quadratic equation using literally any method we've learned except for Desmos, right? So all 5 factoring methods, solving using square roots, completing the square, and quadratic formula, all right? Now, I'm going to try to go pretty quickly through these, but I'm still going to try to explain my decision-making process. Why do I choose one method versus another? So that you can follow through the decision tree. All right, so the first question on the decision tree is there a 0 on one side of the equation? That's good, so we move on. Then we check to see if there's anything in common between these two terms. There is not. 64 doesn't have an x, and x squared doesn't have any number except for 1. So then we go down to how many terms does this thing have? So it's got 2 terms. We're going to go to the 2-term section of the decision tree. And the first part says, are both terms squares with subtraction between? This one's a tricky one because both terms are squares. X squared is the x squared, and 64 would be 8 squared. But because there's not a subtraction between, difference of squares is not an option here. So that brings us to solving using square roots, which is actually easier anyway. Remember that solving using square roots just requires you to move everything over to one side to get the x squared alone, and then we square root both sides. So we can go ahead and minus 64 on both sides. That gives us x squared equals negative 64. Then we need to square root on this side, and obviously we square root to match over here. Don't forget that you have to allow for the positive or negative versions of that. So we would get that x is equal to the positive or negative square root of negative 64. And we can simplify that because the square root of 64 would be 8, and the square root of that negative, basically negative 1, would be an I. And then, of course, the positive or negative versions of that. So that was a pretty quick solve. All right, number 22. Once again, going through the decision tree. Is there a 0 on one side of the equation? Yes, there is. So we move to the next step. Is there anything that all 3 terms have in common? Now, they don't all have a variable, but they are all divisible by 3. So we're going to go ahead and pull that 3 out. And you might remember on the decision tree, since it's a negative leading value, we're going to pull a negative out with it. So we're going to go ahead and grab that negative 3, bring it to the outside. For this term, dividing by negative 3 would leave an x squared. Here, negative 15 divided by negative 3 would leave a positive 5 with an x. And then 72 divided by negative 3 would leave a negative 24. All right, now this negative 3 is just going to sit on the outside for a moment. We're going to focus on the inside now. So now that we've factored out the common term, we can go to the part of the decision tree that says how many terms are there. There are 3 terms. So then the next question is the a value 1? Now, of course, inside the parenthesis, the number in front of x squared is 1. So the decision tree says, let's try reverse FOIL. All right, so we're going to see if this works out. Negative 24 is going to be our multiplication value. Positive 5 is going to be our addition value. So 2 numbers that multiply to make 24, but they add to make 5. So 24 can be 1 times 24, can be 2 times 12, could be 3 times 8. Now, as soon as I hit 3 and 8, I'm like, okay, a 3 and an 8 could make a 5. The only way a 3 and an 8 could make a 5, a positive 5, is if the 3 was negative. All right, so that's our numbers. We've got an 8 and a negative 3. Since this is reverse FOIL, that's it. Those are our numbers, 8 and negative 3. So we can write the factorization then. So the negative 3 is out here. So that would be x plus 8 and x minus 3. Now, we're not done. We actually have to solve the equation. So we have to say, when does x plus 8 equal 0? when does x minus 3 equal 0? And we don't actually have to worry about this negative 3, because if we write the equation negative 3 equals 0, that will just never be true. Like, negative 3 by itself will never be equal to 0. So that one's not actually going to lead to a solution. But each of these other two parentheses, so x plus 8 equals 0, if we minus the 8 over to the other side, that will tell us that x could equal negative 8. And over here, if we add 3 to the other side, that tells us that x could equal 3. So we end up getting two solutions for that one as well. And I never wrote down, I like to write down what we use for that. So that one was, reverse FOIL was the main one, but we actually started with a common factor. So first we divided out that negative 3, then we reverse FOILed. All right, on 23 here, we'll do the decision tree again. So we'll go, is there a 0 on one side of the equation? Yes, there is. So let me go to the next. Is there anything that these two terms have in common? Definitely, right? They both have a 7 in common. They both have an x in common. And then once again, as we've seen a couple times throughout these videos, if the first term has a negative on it, we're going to factor that negative out as well. So we're going to factor out a negative 7x, and we'll see what's left behind. Negative 14 divided by negative 7 would be a 2. X squared, take away an x, would be an x. And then 7 divided by negative 7 would be a minus 1. And an x take away an x means there's no x left. And we saw one of these in the factoring video. Sometimes just doing the common factor, which is all we've done so far, is enough to solve the equation for us. So we have our two parentheses here, our 7x and our 2x minus 1. So we just need to find the solution that goes to each one. So what value of x would make negative 7x equal 0? And what value of x would make 2x minus 1 equal 0? So the first one, that one's pretty easy. That's x equals 0. And then the second one, you would add 1 to the other side. So you'd get 2x equals 1. And then divide by 2. So the other solution would be x equals 1/2. All right, so far, all of these ones that we've done, they've all been pretty quick, right? And so this is the section of the test where you could just use quadratic formula every single time if you wanted to. But some of these are much faster being solved using other methods, specifically 21 and 23, right? And then even with 22, if you didn't factor that negative 3 out and you plug that all into quadratic formula, you're going to have a lot of simplifying that you have to do if you choose to do that with quadratic formula. So I think it's worth your time to at least try some of this stuff out. All right, I'm going to give myself a couple spaces here to to solve these. All right, now 24, we say, we'll go through the decision tree. Is there a 0 on one side? No. There's a 14 on one side. So you might move that 14 over by subtraction. All right. Is there anything in common between all three terms? No. 6 and 14 have something in common, but the first one does not. And the first two have an x in common, but the last one does not. So, so it's three terms. We can try to reverse FOIL really quick. So what are two numbers that multiply to make 14, but they add to make a 6? So that would be 1 and 14. That would be 2 and 7. 1 and 14 cannot add to make a 6, and neither can 2 and 7. So this is our first one where our factoring pattern just didn't really work. Reverse FOIL won't work here. So this is going to be a perfect one to either do quadratic formula for, or because the b value is even, and because the a value is 1, we could use completing the square here. So my personal preference is I'm going to do completing the square. I'm going to go ahead and erase my work. I'm going to erase my work because for completing the square, I actually need that 14 on the other side anyway. So we're going to do x squared minus 6x and then create a space there. And that's equal to 14. And we'll put a space there. We have to figure out what goes in that empty space so that this thing could factor out to be a perfect square trinomial. All right, so we can get this term down here by looking at the middle term here and dividing by 2. So negative 6 divided by 2 is negative 3. And then we can get this term up here, the missing term, by doing negative 3 squared, or negative 3 times negative 3. So that would be plus 9. And on this side, to balance it out, also plus 9. All right, so that means we have x minus 3 squared equals 23. Then we can square root both sides. If we square root this side, it's going to get rid of that square. And if we square root on this side, we have to allow for the positive and negative versions. So that means we have x minus 3 equals the positive or negative square root of 23. We don't really have to simplify 23 because 23 is a prime number. So if you try to break it up, it's not going to break up into anything except for 1 and 23. So then all we have to do is move the 3 over, and we get x equals 3 plus or minus the square root of 23. You could have done that using quadratic formula as well. You might have had to do some simplification. I'm not really sure, but probably you would have to do some type of simplification to get this answer. All right, so that one we chose to use complete the square. You could have used quadratic formula. All right, now number 25. These last two examples are, I want to point something out here. Like, even though the first step of every decision tree is there a 0 on one side of the equation, there are a couple solving methods that we have that actually require us to move things over to the other side. So completing the square was one. We saw that in number 24. We didn't actually need to move that 14 over because we chose to do completing the square. We needed the 14 on the right side. Now, I moved that 14 over. I tried reverse FOIL. It didn't work. And that was when I knew I needed to move the 14 back over. If you look at 25 here, I can identify right off the bat, without moving that thing over, that this one's going to be solvable using just the square roots property. So I'm actually not going to follow the decision tree thing, the decision tree like box that says get a 0 on one side, because I'm already looking at this and thinking I can just divide the 4 over and square root on both sides. Since this equation is easy enough to identify that right away, I'm not going to follow the decision tree boxes, okay? So we've got 4x squared equals 25. We're going to divide by 4 on both sides. So that gives us x squared equals 25 over 4. And then we square root on both sides. So that gives us the positive and negative square root of 25 over 4. Now this is a special one. You can actually simplify this very easily because both 25 and 4 are square rootable. So the square root of 25 is 5 and the square root of 4 is 2. So the answers here are just x equals positive or negative 5 over 2. All right, now 26. 26 has 3 different terms. So I am going to follow the decision tree on this one. All right, so first step, is there a 0 on one side? No. I like to have a positive a value when I'm solving. So instead of moving the 2x squared over here, I'm going to go ahead and move the 12x and the 21 over to the left side. So that's going to give us 2x squared minus 12x and plus 21. All right, now you can already see because the a value is not 1, this is going to be an AC method, or it's going to be a quadratic formula. I'm quite positive there's a quadratic formula one coming up soon. So I'm going to go ahead and do AC method on this one and just see if it works. So 2 times 21 is 42. Now I'm looking for two numbers that multiply to make 42, but they add to make a negative 12. So 42 would be 1 and 42. 2 and 21. You can obviously do this with your calculator if you need to, but 3 and 14. 4 and 5 aren't going to work, so then we'll go 6 and 7. Oh, 6, 7. Let's see. Do any of these combinations add or subtract to make a 12? It doesn't look like it. So this one might be something we have to use quadratic formula for. And for myself, I'm okay spending a little bit of time checking to make sure. But once I know that AC method isn't going to work, I'm just going to go straight to quadratic formula then. So A is 2, B is negative 12, C is 21. So x would equal negative 12 plus or minus the square root of that negative 12 squared minus 4 times the a, which is 2, times the c, which is 21, all over 2 times that a value, which is 2. All right, you got a lot of simplification to do here. So negative 12 is 12. Inside the square root there, you can go ahead and do that in your calculator if you want to, but negative 12 squared is 144. And then 21 times 4 would be 84, and 84 times 2 would be 168. And that's going to be a minus 168. So now we have 144 minus 168. I'm kind of running out of room here, so I'm going to go ahead and erase this part and keep going up here. So x equals 12 plus or minus. Now 144 minus 168, that's going to be the square root of negative 24. And anytime you have the square root of a negative in here, you're going to have to simplify this yourself, probably, because a lot of us have calculators that won't do that. So the negative inside the square root, that's going to come out as an I. So go ahead and set that I on the outside here. And then 24 can be broken up into a 4 times 6. That 4 can come outside of the square root, which would give us 12 plus or minus. When that 4 comes outside, it becomes a 2, because the square root of 4 is 2. All right, and what this does is this allows us to do a little bit of canceling here. So the 12 and the 2 and the 4 are all divisible by 2. So this is going to cancel to 6. This is going to cancel to a 1. And this is going to cancel to a 2. So the final answer here would be x equals 6 plus or minus I times root 6 over 2. All right, that one, we had no choice. We had to use quadratic formula. But you can see how much simplification there is with quadratic formula sometimes. So I'm hoping one of these last ones here will be something we can do an AC method on. Maybe this next one we'll be able to do. All right, 27. Is there a 0 on one side? No. So let's bring that negative 18x over. So that would give us 9x squared plus 18x after we move it over, minus 7, and that equals 0. All right, because the a value is not 1, the only way factoring is going to work here is if we do AC method. So I'm going to go ahead and check this out really quick. 9 times negative 7 makes negative 63. Then we have to do negative 63 here. That's the multiplication number. And the addition number is 18. All right, so 63 can be a 1 and 63, a 3 and a 21, a 7 and a 9, obviously, we already did that. All right, so it looks like the 3 and the 21 are going to be the magic numbers here. So in order for it to be a plus 18, that's going to have to be a negative 3 and a 21. All right, so I'm going to erase this, give me some space. -3 and 21 are the magic numbers. So that means this is going to get split up into a -3x and a positive 21x. Then we do grouping to finish out the AC method. So in the first pair of two, we have a 3 and an x in common, which leaves behind a 3x minus 1. And in the second set of two, we have a 7 in common, which leaves behind a 3x minus 1. All right, so that means this all factors out to be 3x plus 7 times 3x minus 1. All right, now we're not done. I ran out of space, but we have to solve this. We have to tell what x values actually make this equal 0. So for each parenthesis, we need to know when is that parenthesis equal to 0. So when is 3x plus 7 equal to 0, and when is 3x minus 1 equal to 0. So you just solve each of these equations. So you would minus the 7 over and then divide by 3. So we're going to have one answer is x equals -7/3. Over to solve this one, you would add the 1 and then divide by 3, which would give us x equals 1/3. All right, I used AC method to solve that. You may choose to use quadratic formula for that. All right, number 28. Is there a 0 on one side? Yes, there is. Is there anything in common between these numbers? Yes, there is. We can factor out at least a 2. So let's take that 2 out. That gives us 9x squared minus 12x plus 4. Okay, once again, we could do AC method with this. This time, though, I think I'm just going to go for quadratic formula. And that's mostly because I just want to show a couple more examples of quadratic formula, at least one more example. So our A value is 9, B value is -12, C value is 4. All right, so x equals -12 plus or minus the square root of that -12 squared minus the 4 times the 9 times the 4. All over 2 times 9. So -12 gives us 12. Inside the square root, we're going to have 144 on one side. And then the other side, 4 times 9 is 36. 36 times 4, that actually ends up being 144 as well. And, of course, on the bottom is 18. So that means what's inside the square root here is 0. 144 minus 144. That's kind of unique because that means that the whole square root part of this equation just equals 0. That means that this plus or minus, the whole square root thing, it's all just nothing. So actually it's just 12 over 18. X equals 12 over 18. We can simplify that, divide the top and bottom by 6, and this is a very unique parabola or quadratic equation that just has one solution. X equals 2/3. So maybe we saw that coming, but maybe not. That doesn't happen very often. It has to be very specific to get those numbers inside the square root to cancel out like that. All right, let's finish up this section. Number 29. Is there a 0 on one side? Yes, there is. Okay, we're good there. Is there anything in common between the two terms? 27 and 4 don't have anything in common, so we're ready to solve. There's two terms. You might be tempted to think that this is a difference of squares one, but, because of 4 is a perfect square and x squared is a perfect square, but then 27 is not a perfect square. So this one's just going to be a solve using square roots problem. So move everything over to one side. So let's minus the 27 over. That gives us -27 equals 4x squared. Divide by 4 on both sides gives -27 over 4 equals x squared. and then square root both sides. So that would give us, oh, I made a mistake there, didn't I? There was supposed to be a negative on the 4 right here. All right, so what that's going to do is that's going to turn that into a positive 27 over 4. All right. And then whenever you introduce the square root, don't forget your plus and minus. All right, so x is equal to the positive or negative square root of 27 over 4, which you can actually simplify by doing the square root of 4 on the bottom, which would just become 2. And then the square root of 27 on top would simplify to be 3 square root 3. So the best and simplest version of the answer would be positive or negative 3 square root 3 over 2. All right, well, let's just finish up 30 and 31 here. That's probably about as much as I'm going to get done this year. Hopefully the rest of the review you can figure out the Desmos and the projectile motion and things like that. So number 30 and 31 basically ask us to do the exact opposite of what we've been doing. Rather than giving us a quadratic function and telling us to find the zeros or find the solutions, they give us the zeros, they give us the solutions, and they say build the equation. So this is actually pretty easy. Anytime the zeros are integers, this is really, really easy, because each of these values, the -3 and the 3, it had to come from a parenthesis. And as you've noticed in our solving up here, every single time we have a parenthesis, like in number 27, each parenthesis leads to an answer, right? And then let me scroll up a little farther. In number 22, when we had 2 parentheses here, each one of those parentheses led to an answer. In number 23, same thing. We had 2 parentheses, each one led to an answer. So when we're going backwards, if we know the solutions are x equals -3 and x equals 3, all we need to do is come up with the parenthesis that those answers came from. So H parenthesis will be like an x plus or minus something. So if we want to make a parenthesis where x equals -3 would be the answer, we would have to put inside there x plus 3. Because when you plug -3 into x, the -3 plus the 3 makes the 0. And that's what we're dealing with here. We're dealing with zeros. So that first parenthesis would be x plus 3. The second parenthesis would be x minus 3. So to get the quadratic function then, we just have to multiply those two together. So x plus 3 times x minus 3. Using our foiling pattern, x times x would be x squared. The middle term would be these two numbers added together. Well, guess what? Plus 3 and minus 3 are going to cancel out to be 0x. So we don't have to write an x. And then the last term is going to be these two multiplied together. So that's plus 3 and minus 3. Positive 3 times -3 is x squared minus 9. All right, cool. 31, a little bit harder, simply because of the fraction. So you can say, all right, it's like our answers are x equals 1/2 and x equals -4. So this parenthesis here would be x plus 4, so that the -4 would create a 0 there. And you could just write this parenthesis as x minus 1/2, because if you plug 1/2 in for x, it creates a 0. The annoying thing about this is that now you have a fraction in your equation, right? So when you FOIL it out, you have to deal with fractions now. There's actually another way to do this, and it takes a little bit of thought. Essentially what you do is you move these pieces over, so the 2 and the 1, you move them back over to the other side to find out where it came from. So if we wanted to move the 2 back over to this side, since the 2 we're dividing by 2 now, we could actually multiply that 2 back over to the other side, which would give us 2x equals 1. And then if we wanted to move the 1 over to that side, we could subtract the 1 over, and that would give us 2x minus 1. So instead of writing x minus a half, one of the ways you could write that so that you don't have to deal with a fraction is 2x minus 1. So that way when you multiply it all out, you can actually FOIL it out and not have to deal with fractions. So 2x times x is 2x squared. 2x times a positive 4 is 8x. Negative 1 times x is negative x. Negative 1 times 4 is negative 4. So your final answer here would be 2x squared plus 7x minus 4. That thing would factor out to be these parentheses right here, and each parenthesis would lead to an answer like that.